is Tom Skazort, and this is my explanation video for Assignment 1, Machine Learning Basics for Intro to Neural Networks. So first thing we want to do is exercise 1, where we're inspecting a data set. So obviously first thing we want to do is import sklearn and matplotlib, because these are the libraries that we're going to be using throughout the entire thing. What this is doing is this is loading the diabetes data set that we're going to be using. We store this into an x and a y value because we have return xy as true, and it returns a tuple, I guess. And this is the shape of the data sets. So as you can see, for diabetes X, this is a 10-dimensional shape, and it's kind of hard to plot a 10D array. So what we do is we decompose this into 2 dimensions using this formula that was given to us. And as we can see now, it's 2D, so we're good. We're trying to graph this using matplotlib. So we do this by getting a plotlib subplot, putting it into AX, making this scatter with the first dimension and the second dimension of X 2D. Set the labels, and then we get this graph. Now this is a pretty good graph, but the problem is it's numerical and not categorical, meaning that it's not a binary like 1 or 0 or 1 or -1. It's a bunch of different values, and it's a lot harder to do training on things like that. So what we're going to do is we're going to make the graph look like this by making it so that any value above the average is denoted with a +1 and a plus, as you can see here, and any value below the average is denoted with a -x. So we do this by doing a what is it called in Python, a list comprehension, basically saying it's 1 if it's greater than the mean, else it's -1 for everything in the y value of diabetes y. And then we get this graph, or this array, I mean. So -1s means that it's less than the average, and +1s means that it's above the average. Then we just graph the data set again, making it so that if the y binary is 1 for both of these, the marker is a plus and it's positive, and if it's -1, it's an x, it's negative. Print out the labels, and we get this graph. Looks great. Now for exercise 2, we're doing bias variance trade-off. We start with this code to generate a 1D data set, and this is just generating this data set. This is it's just generating the data set, and then we can see the shape. It's 1D because it doesn't have anything over here. 75, 75, perfect. What this is doing is it is getting a random seed. Seed is 42 because it's the answer to life, the universe, and everything. We get the random seed, and then what this is doing is this is splitting the data into our training data and our testing data. So we have this as 33%, which means the test size is going to be 33% of the total, which is a 25-50 split, which is what we wanted. That's what was asked for. We reshape the data. I'm honestly not really sure why we have to do this. It seems like it's just for using this library. I was trying it first when I was doing it, and I was very confused, but it said, hey, you got to reshape the data. So we reshape the data. That's what this is doing. And we check the dimensions again, and we see we got what we wanted: 50 for the training, 25 for the testing, and it all looks good. So then we import our linear regression model. Machine learning is that easy. You just call linear regression. That's all it takes. Luckily, we have these built-in functions to do it all for us. So we fit a linear model to our training data, and we get the coefficient and the intercepts here. We want to see the training error and the testing error, so we just call this built-in function lr_score on both of them, and we can see the training error is this, and the test error is this. And we want to graph something that looks like this. So these are the functions of ordinal linear regression. Luckily, we don't have to actually implement these because they've already done it for us. And this is ridge regression. This is ordinal regression. So we just do this function to get this ridge regression, and we put this into here. This is getting the scatter data earlier. This fitted line is this line right here. What this is doing is essentially the slope formula. So y equals mx plus b. So you have your coefficient, that's m, I is x, plus the intercept, which is b, and then it's doing that for everything in the training data, and then it's reshaping it so that we can put it in here. Again, I'm not really sure why we need to reshape it. That's something I need to look into more, I think. We plot this line, this line right here, and then we just put the labels on here, and we get something that looks like this. Looks great. All right, and then now what we want to do after this is we want to do it for different levels of alpha. Now what alpha is, let me just look this up again so that I can be confident in what I'm saying. Alpha is the learning rate. So essentially, if it's too low, it's going to be making multiple small learning rates. It's going to take a lot longer. You want one that's just right, like the one in the middle, gets there perfectly to the minimum point. And if you have it too high, it's going to be making too far of leaps, and it's not going to be able to find it perfectly, and it's going to make divergent behaviors is the term that it uses. So we iterate over these different alphas, and then we just plot it all over again. This is the same kind of plot thing that we were using earlier, except we use the ridge, because I don't think we did that before. Yeah, we're using this ridge regression this time. We're getting the training area, and then we're plotting it so we can see here. This is what it looks like. This is the original. This is alpha 100. This is alpha 1000. And so it looks like, as you can see, as the alpha increases, the error on both the training and the test actually decreases. Now, conceptually, this doesn't really make sense to me, because it should be that if your alpha is too high, like I said in this graph, if we want to look at it again, it's going to be diverging too much. But I wonder if it's just not too high and it really is more like this middle one. And I'm curious to see if I were to put like 10,000 or 100,000 as alpha, if we would start seeing it go back up, the error rate. I have a feeling we probably would, but I think that that's probably what's happening, is that 1,000 is actually a pretty good value for the alpha that we're using, since the training error and the test error is going down. So yeah, that is assignment one, the solution to it. Yeah, this is my explanation.